right, first, thanks for having me here today. I'm Rizzo. I am I started this project nigh on like four and a half years ago at this point. I hold a few roles. I manage the engineering teams at Google that are contributing to OpenTitan, but I also serve on the low-risk board of directors as well as the elected project director per our technical charter for this project. So I'm going to talk about OpenTitan today and how we're going about producing the world's first commercially available open source silicon root of trust. So yeah, that's the kind of the first thing we're producing, but really what I'm going to talk about is kind of how to build a coherent open source silicon ecosystem. There's the agenda. I've only got 20 minutes. I'm not going to read that. So first off, background, kind of what are we doing? What is this? So what we're building today is this open source silicon root of trust. And we're really guided by these three core values: transparency, flexibility, and quality. And then I'll talk about how we actually ground those out in reality, so it's not just marketing speak in a little bit. So transparency is primal to our project. It's a core pillar, but you can't really build commercial silicon today in a fully transparent fashion. There's a clear foundry boundary. So what we're doing is we're lowering the transparency as far as we can go while still operating in a modern node to build something commercially viable. So what it means is basically any time we can make something open source, we definitely do make it open source. So it's not just the RTL, it's also our design verification IP. I know for a fact that people are picking up both the entire project, but also bits and pieces of it and integrating it into their designs. So we view that as a real sign of success. So where we're at today, we've got this first piece of discrete silicon arriving, mid to late 2023, and then we're moving on to, well, actually simultaneously, we're working on an integrated root of trust designs, as well as something we call multi-top, which is, I don't know, I want to call it like version control for silicon IP. And then I'm going to present real quickly at the end, if we get to it, some of our initial post-quantum verified boot results. All right, so just quick digression. When I say open, I mean it in implementation and process. That second open is an actual GitHub link. So while it's pretty easy to claim open source, it's a really different thing to actually design, develop, and maintain a silicon project in the open. It's taken probably 60 people, 4 or 5 years to actually get to this point. So it is a really effort-intensive thing. So it's not someday, it's today. It's not a promise. There's an actual repo. It's not an open standard. OpenTitan is an actual implementation because the transparency of the design is crucial. And we're not really looking for a lot of different interpretations. And this was not developed in some proprietary manner and then kicked over the wall with no support. So what I'll talk about next is our partners, including Low Risk, which is the actual kind of hosting and overseeing organization for OpenTitan. So all of these partners are contributing financially and in an engineering sense to OpenTitan and Low Risk today. And this is what really sets this project apart is we have a built-in ongoing support mechanism. So Low Risk is here. I highly recommend stopping by their booth and seeing their demo of OpenTitan running. But what Low Risk really provides is this hosting and infrastructure collateral called the Silicon Commons, right? This is the shared infrastructure so that all these diverse parties can participate and contribute. And it's one of the things that really sets OpenTitan apart as an open silicon project, that and our copious design verification IP, which is also freely available. So all these partners together are really contributing unique pieces to what makes, what is necessary to make an open source silicon root of trust. It's not just the partners, it's actually about having an open active ecosystem as well. So it's not just a bunch of commits over time, it's, every month you look at, and I just pulled this, I don't know, about an hour ago, every single month looks like this, right? It is hundreds of pull requests, it's hundreds of issues and tasks being assigned, and it's an ever-changing set of people who are authoring commits for this project, but it is consistently a high number of people. And I think I see a number of those people who are listed there, back there, so definitely stop by the booth and say hello. So I'm going to talk a little bit about what the technology is that we've developed, and that is available in that repository today. So we're organized as a set of silicon security software working groups. I'm going to talk about a fourth sort of cross-cutting concern, which is infrastructure. And this is really a snapshot of the technology that we've developed today. So this is our first discrete top-level design. It's called Earl Grey. Low risk is a Cambridge spinout. We went with a T-themed top-level naming scheme because we're cute like that. One of the big interesting pieces of this OpenTitan design is actually the IBEX core. It's an RV32 IMC partial B. Someone will correct me later, I'm sure. That is finding common use in many, many, many different designs. So this was formerly the zero risky design, but we worked with Luca's lab at ETH Zurich to actually pull that into low risk and sort of have a long-standing sort of team developing and maintaining that. So this includes all the various IP you'd expect in any root of trust. Most roots of trust, when you squint, they have a lot of common functionality, which is actually one of the reasons we've been able to move forward so quickly on the integrated version of OpenTitan at the same time as we're developing the discrete version of OpenTitan. And where we're at today is all of our blocks are at what we call a D2 V2 stage, which basically means that the open source design is functionally complete, and the DV coverage metrics are all over 90% or greater, modulo a few waivers. So that means that it's really now up to our backend partner, Nuvoton, to take that design, do the Foundry integration, and actually produce the tape out in the next year. So for security, we have a complete published model for a secure microcontroller. I assure you the documentation is complete, even if it's not necessarily organized. So if you dig long enough, you will find a lot of interesting information that covers really the full life cycle of a secure silicon design. We have a set of hardened cryptographic accelerators, so we harden against not even common SCA or side channel analysis and fault injection attacks, but we are hardening these to a level where in both hardware and software countermeasures, if you're familiar with common criteria, we're targeting what's called AVA Van 5. So that's basically a secure element level of hardening. So we work closely with third-party labs to evaluate and iterate on our secure IP. And of course, we're also developing a set of in-house tools that are pretty targeted towards the new AE family of chip whisperer boards and chip shouter fault injection stuff developed by new AE, a low-risk subsidiary. So on software, we do significantly more than just boot ROM extension development. It's test suite, things we call device interface functions, which are used to construct a lot of our top-level DV test suite. We also have a hardened cryptography library, as well as a kind of standard comprehensive host-side support for a thing called OpenTitan tool, which is basically a Swiss Army knife to support OpenTitan designs. And then, of course, our build system, where we are moving, well, we have moved our software to Bazel, and it all works perfectly, and there are never any complaints. So on infrastructure, this is a really cross-cutting component of what we're developing today. We run CI to maintain a healthy code and it's very constantly evolving code base. We track coverage metrics, and then we have kind of matched pre and post silicon testing. We also enforce quality standards through linting, but also via policy methods with our coding style guides, code review, kind of standard open source development processes. So the technology is important, but it's really just one component, one output of this successful ecosystem. We're kind of trying to square two very difficult facts. We have a distributed, physically, organizationally, culturally team in a traditionally proprietary space of silicon, working in a very specialized domain of secure silicon. Second fact is that commercial silicon is generally the result of a highly coordinated, for some definition of coordinated, resource-intensive effort over a long period of time constant on the order of years, not months or weeks. And so we have to take those two things and kind of square them together and coordinate all of this effort of all these different partners and contributors of this diverse team to be able to actually develop a complete end-to-end silicon design. So we do this via process and infrastructure. This is really the Silicon Commons, which is kind of the catch-all term for all of these aggregate technology processes, organizational techniques that we use to develop and mature our silicon IP and the overall top-level designs. So one aspect of this, and I'm just going to touch on a few at random. There's a lot more than this, but these are kind of the ones that I had graphics available for. So hardware development stages, we take everything through a very structured development process. And at the end of each of these arrows and the start of the next arrow, there is a review process. So everything is double, triple checked, and checklists get made, issues that are identified are resolved, and then the IP moves to the next stage. And then after that, we have the continuous integration infrastructure. This is, again, one of the ways in which we keep code quality high. Yeah, I wouldn't say it's a standard continuous integration infrastructure, but it is one that has worked for us for a period of time, which leads to kind of our nightly regressions and our on-call rotation policy. So we kind of spread this burden of doing on-call regression across partners so that there's always usually 2 individuals responsible for going through regressions. And they don't have to solve them necessarily, but they do have to triage them. So that's how we drive this curve of regressions just happen. And this is how we drive that to getting a green code health pretty much at all periods of time. So where are we at today? So there are some unique opportunities along with all the challenges that come with doing a real open source silicon design. It enables an ecosystem, not just a device. It serves as a platform for research, but also for commercial innovation and impact. Because we're working in this very specialized domain, having this open design gives us a place to really concentrate specialized effort on hard problems where correctness matters. If you talk to enough cryptographers, you kind of eventually realize that they really are not looking for yet another crypto library. They really like to have one crypto library where they can focus because it's hard enough to get it right. And then obviously one of the big things of something like OpenTitan is to reduce this leap of faith we have to take on some of our most foundational security guarantees. So certain of our partners, including my employer, are very interested in this because we would really like to buy things off the shelf that kind of inherently meet our security requirements. So just really quickly, I'm going to talk about kind of where we're headed and some recent results that we've gotten that are very interesting. One is that we sort of we were given and took some very good advice very early in the project, and we implemented a Ketchak or SHA-3 hardware accelerator, which has actually enabled us to, without any hardware changes, implement a performant version of Sphinx Plus, which is one of the NIST standardization candidates for post-quantum verified code. So we are now at a point where we are actively considering and very likely will ship with this, not necessarily enabled by default, but as an option in our first engineering sample silicon next year, because we want to get it built and evaluate it. So that's very exciting. This actually came together very quickly as a result of a collaboration from my cryptographer, Jade Philippum, and Peter Schwabe, who is responsible for developing a lot of these algorithms. So this is a very exciting result, and we're quite happy to be able to be exploring this and have a credible implementation of a stateless signing scheme. So on the sort of adoption of OpenTitan as a platform and use for research, we ourselves are involved in a number of collaborations, but also we have had people kind of find OpenTitan on their own and use it to develop new hardware security technologies or evaluation methods, which is really great for us because what it means is that we've effectively shortened the time between something interesting being found in the lab and when we can actually deploy it in first silicon, because this just sits there and serves as a platform that people can develop on, which has been very, very exciting. It's one of those things that I thought would happen or I predicted would happen, and it sounded really good, and then it actually did happen, so that was very exciting. And And then there's also been a number of examples of OpenTitan serving as a commercial innovation platform. So the big one is obviously Nuvoton working with us to actually tape this out and deliver commercial silicon, which will go into major products and that we already have consumers for. But also, the baseline that we've built has been so high quality that even folks like Microsoft have adopted it and have started developing, or have already developed, Cherry, which is a tagged architecture extension on top of the IBEX core, which is very, very interesting. And then a number of folks have made their IP compatible with OpenTitan. Obviously, we don't require any proprietary IP beyond the Foundry stuff, but it is interesting that they are adapting their IP to work with our root of trust technology. So that's, I'm happy to say I'm going to have 5 minutes to leave for questions after this final statement of, well, why are we doing this? The reason that we are doing this is, one, we want to improve security industry-wide, doing it in a high-quality fashion and then giving it away with some trademark enforcement attached to it to make sure that it is what it says it is one way to do that. And another is because, this being the RISC-V conference, my view is that this open ISA is basically inevitable, so let's lean into it. And then let's figure out a way to use this so that it's, once it exists, it just becomes a question of, well, not why would you use open silicon, but why wouldn't you use open silicon, right? And the way to do that is to actually build it and show that it works, and we are well down that path. And with that, I am happy to take questions for 3.5, 4 minutes.
Yep, so there's no questions from the online audience, but over here, questions?
Hello, thank you for the presentation. Regarding the roadmap of OpenTitan project, is it available somewhere? Can we find it somewhere, or have any comments on that? We want to see how it will...
The roadmap?
Yeah.
Oh, roadmaps cost money. So our partners are our roadmap, but we don't publish a formal roadmap. I can tell you that we're obviously doing the discrete first, and then we're moving into an integrated one, and all that work is happening out in the open. But we generally, I propose a roadmap every year as the project director that gets voted on by the steering committee. I have not done one for 2023 yet, and if history is any guide, that will happen in June. But yeah, we don't really publish a roadmap. So, okay. But we're gonna be plenty occupied for the next few years between discrete, integrated, and some variants of integrated. We've got this notion of there's not gonna be just one integrated root of trust solution, so we're gonna be developing many of those over time as we meet various sort of application needs.
I saw in your website that initially it was mentioned that OpenTitan is used only as a root of trust for applications, and the use cases they were like second factor authentication, smart cards, and these kind of things. But now there's also the TPM included, and this is quite interesting. And
well, we made sure that it was. So these are all just applications, right? We keep saying it's a root of trust, but it's just a secure microcontroller that can function as a root of trust. Something like TPM, passive measurement, root of trust for measurement, a little bit of sealed storage, things like that. It's just an API thing. The only actual hardware change is you have to do like an in-band flow control because it takes a while to generate keys, right? So we threw that into our SPI, Tim? Yeah, SPI? Yeah, we threw that into our SPI controller. So it is by default, because someone might want to make this a TPM at some point, right? Nuvoton is a major TPM vendor. It didn't hurt us any to do that, so we just did that. But I am aggressively agnostic to APIs because there are so many different root of trust APIs out there for all these different applications, and I'm not going to be choosing one API to rule them all, because that's how you end up with one more API.
So just a quick question as to why not use open silicon? We're in a room full of companies that can enable open silicon. What were the barriers? What makes it hard to use open silicon today?
People don't think it's going to work, which I find bizarre, because there is a GitHub and it definitely works. So I don't know why you wouldn't use open silicon today. I guess it takes 5 years to develop it, and most people are selling most people who are making silicon are selling silicon, they're not selling ads, so maybe because we had the luxury of kind of taking a strategic view, right? So that's why. Or that's a reason, that's a good reason why, is people got mortgages.
Has FIPS been part of the discussion on this?
Like, are we talking to NIST, or do we make this FIPS compatible by default? Yes. So so we take certification very, very seriously, and we, having had the personal experience of trying to retrofit FIPS onto something that wasn't designed with FIPS from the start, we put that in there as a requirement from the start. So all of the IP that we develop and the system design is all FIPS 140-3able, great. But we actually also are, like I said, targeting certain common criteria protection profiles, PP00084, PP0084, whatever. So that's kind of the secure element one. We're also targeting this new S3, or it's not called S3 anymore, it's called PP0117, which is integrated secure element for various apps. So we take those things seriously from the start, which infuriates my silicon lead, even though he is too polite to say that. You're nodding, right?
So I think we are out of time for more questions, so thank you very much.
Happy to give the talk.